All right, thank you very much for coming this evening. My name is Jonathan Heiliger with Facebook. Work in technical operations and infrastructure here. Tonight we're going to talk to you a little bit about rethinking servers and data centers and what that means. I think the fundamental point of the talk is that there's lots of new approaches and lots of old ones and lots of existing best practices, and we're not going to chronicle all of the ways in which you could do things, but hopefully suggest some new ideas and suggest some things that we're doing ourselves that you can take back and consider in your own businesses. And the best part is I'm actually not giving this talk. One of my colleagues, Amir Michael, is going to give this talk. So you'll get to hear from a real expert and not some overhead guy. Just a little bit of background on Amir. Amir began his career in the trenches, really building servers, building technologies, and actually installing these servers at another large internet company down in Mountain View. He's since moved on to solving other problems in the data center, and has been able to bridge both an electrical engineering and computer engineering background in a pretty unique way that gives him visibility into both the problems and opportunities on the server side, as well as the problems and opportunities in the data center itself. And that's fundamentally why he's here working on these problems for us. So with that, I'd like to bring Amir up, and I think what we're going to do is have him give the talk and then have Q&A at the end there's a bunch of Facebook people around here to talk about sort of the things we're doing, and then hopefully spark a discussion with you guys. Thanks again for coming.
Thanks, Jonathan. Thanks, everyone, for coming. My name's Amir Michael. I've been at Facebook for about 7 months now, working on servers and data centers and coming up with ways to optimize those systems. So today, I'm going to give you a little bit of a talk about our approach to servers and data centers and how our unique culture here at Facebook allows us to think differently about these systems. To think differently and develop them in ways which are a little bit more non-traditional. Before I get into that, let me give you a little bit of an overview about what people do on Facebook. So collectively, people spend 8 billion minutes every day on Facebook. In the US alone, Facebook is the #1 site as far as time spent. Over 2 billion pieces of content are shared every week on Facebook. Now, content can be a lot of different things. It can be photos which are uploaded, status messages, people commenting on other people's statuses, all of those types of things. This happens about 2 billion times every week. And we have over 2 billion photos uploaded to the site each month. We have a little bit over 20 billion photos right now, and we're adding 2 billion every month, and this is growing. These are photos of people's parties, people's events, every different type of thing. We get lots of different photos on the site. There are 15,000 Facebook Connect implementations. What does this mean? It means that there's 15,000 different people or applications or devices using our API. We get about 5 billion API calls to Facebook Connect every day. One example of this is the just announced integration with Xbox today that's using Facebook Connect. So we also just announced a couple months ago that we crossed the 300 million user mark. So it's basically, the site's seen pretty explosive growth to the point where the curve looks almost exponential. Now, coming from the operations side of things, as someone who needs to think about how we deploy servers and how we deploy data centers in order to meet all this demand, this can look a little bit scary. So what we do at Facebook is we try and solve this problem by not having to grow our infrastructure in this same proportion, according to this curve. We want to flatten out the curve. And we're trying to do this on a couple different fronts. One of them is through software, which is basically optimizing our software so that it runs more efficiently on our servers, so that we don't have to follow this type of curve. Now, the second part, the second phase in which we're trying to attack this same problem is by looking at the infrastructure itself, by looking at the data centers and looking at the servers. and trying to realize how we can do these things a little bit differently and a little bit more efficiently so that we don't have to grow it in this same type of scale. Our goal is to grow it in a much flatter curve. And ideally, our ultimate goal is to reduce the cost of this infrastructure per user. So for every additional user that we get on the site, we have to spend less money on infrastructure. So how does this affect hardware? Obviously, as we get more users, we are deploying more hardware. So let me share some of those numbers with you. All right, I really wanted to show you numbers. Every engineer likes to tout how much horsepower they have. Unfortunately, I couldn't get that number. Being a private company, we don't really share this type of information. And I can't even guarantee that the X's represent the actual number of digits that we would have for each one of these. But we have a ton of hardware. So does this look familiar to anyone? So this is what a typical data center would look like. Let me sort of give you a little bit of an overview of what a data center is. So companies who run large websites needs lots of servers. What's a server? Server is basically a motherboard, a CPU with different types of storage on there. It could be RAM, could be flash, could be disk. We have different types of servers. Some of them are geared more for compute, so they have a lot of CPU on them. Some of them are geared more for storage, so they have lots of disks. And some of them are geared for very quick access to database features, so lots of RAM. We like to serve things out of RAM because it's much faster. Users tend to use the site more when it's more responsive. So we have a couple different types of servers that we like to deploy. Now these servers, when you have so many of them, you need to house them. And a great way to house them is to put them in a warehouse. Now, these servers are large heaters. They generate lots of heat. So in this warehouse where you now put your servers, you need lots of equipment to remove the heat from there. So you have things like chillers, air handlers, all sorts of other devices in there which remove the heat. Now these devices also consume a lot of power. So you need a lot of power distribution inside this warehouse as well to get the power to the servers. And in a sense, you're no longer in a warehouse. You're now in something which we all like to call a data center. So let me give you a little bit of an overview of how a traditional data center operates. There's many companies out there which build these cookie-cutter data centers one after the other and lease space to customers, internet companies, or any other type of company who needs to have a large pool of servers. This is what a traditional power distribution scheme looks like. The top layer is really the high to medium voltage conversion. Now, there are lots of power utilities, and the power utility will supply power directly to the data center. And they distribute this power at a high voltage, around 120,000 kilovolts, sometimes even more. The power comes from a generation site. Could be coal, it could be nuclear, could be hydroelectric. And the data centers aren't typically located very close to these facilities. So the power is distributed at higher voltage, so you get less loss. Now, just to give you an idea of how much power a data center may require from a utility, a typical size data center on average can maybe be around 15 megawatts or so, which is enough power for about 15,000 homes. Small community, small city. Now, this power is distributed, and eventually, when it gets near the data center, we build a substation. The substation takes this high voltage and converts it down to lower voltages, anywhere between 35 and 12.5 kilovolts at this point. From there, it goes to something called site transformers, or several site transformers. And these are just transformers which do the same type of thing as a substation. They take the high voltage and they convert it down to an even more usable level. The high to medium voltage conversion systems typically have losses on the order of 2 to 3%. Now, data center operators, depending on what kind of contract they have with the utility, pay for the energy entering the substation. So any improvements made to the substation or the site transformers end up paying back to the operator. So if you're able to make more efficient substations or transformers, you can typically end up saving costs there. Now, the next system is a UPS system, or an uninterruptible power supply. So the UPS has a very specific function. A data center needs to operate 24/7. If the utility experiences a blackout, we need to maintain the servers so that they don't power off. Our users are all over the world, and if we have a power disruption somewhere, we still need to be able to run traffic to all of these users worldwide. So the uninterruptible power supply stores enough energy in batteries to keep the servers running for about 6 minutes. 6 minutes is enough because the data center also has generators sprinkled around the building, and a generator is basically a large diesel engine with a generator on there, and it burns the diesel fuel, creates electricity, and then we power the servers with that. And the generators typically take about 8 seconds to come online. And so the UPS's role is mainly to keep the servers online until the generator kicks in 8 seconds later. Now, a UPS has a couple components. It has an AC to DC rectifier. From the utility, we get AC voltage, but batteries need DC. So the rectifier takes the AC voltage, converts it to DC. We charge the batteries, and then we take the voltage from the batteries at 540 volts, put it through an inverter, and it goes back to AC, because that's what the servers ultimately will use, AC voltage. So a typical UPS can have anywhere between 8 and 12% loss. There are today more advanced UPSs which only have around 1% loss. They're not very common in the industry just yet. Now, from the UPS, we go to something called a PDU, or a power distribution unit. These are sprinkled around the data center, and they have large pipes coming in with lots of electricity, and they fan out the electricity to smaller, more manageable pipes. Now, a PDU also typically has a transformer in there. It takes the 480 volts from the UPS, converts it down to something a little bit more usable, around 208 volts. And because of this transformation, and because we're now distributing voltage, power at a lower voltage, we have losses associated with that. And there's anywhere between 2 and 4% loss in the distribution throughout the site and in the PDU as well. Finally, after the PDU, we get to the server itself. The servers are organized in racks, and they'll have a power strip in there. And the power strip will then deliver power to the server itself. Now, the server has a power supply, which does something similar to the rectifier. It takes AC to DC, and it outputs typically 3 voltages, 12, 5, and 3.3 volts. Server power supply. In the industry today, we typically are seeing around 85% efficiency from these devices. So 15% of the energy is actually burned up in heat. From there, the power finally gets to the motherboard, and the motherboard has VRMs or VRDs on there. These are more voltage regulation devices, which take the 12, 5, and 3.3 volts and convert the voltage down to something that's more usable by the components. Now, the components are what we really care about. That's what does the actual work for us. That's the CPU, the memory, the disks. Motherboard VRMs, which do this conversion, are typically around 90% efficient as well. So if we look at this entire system, the green bar on top, most of this equipment's located outside of the building. The rest of it is located inside the building. And so what does that mean? All this heat that's burned up in the inefficiencies of these systems, we now need to cool. And so we're spending more energy cooling all these inefficiencies, all this heat that's burned up inside of the building. If you look at this system, the total losses are around 35%. So from the input, from the utility, until we actually get power to the components, we've lost 35% of the energy. So this is one of the problems that we're facing here within operations. How do we make this better? How do we make it more efficient? So I'll describe a little bit about what a traditional cooling model looks like as well. Servers, if you can imagine them, look sort of like pizza boxes. They're flat. Inside of them, they have components, motherboards, CPUs, memory. And they also have fans which draw air through the server. The fans are needed to cool the components inside the servers because the components are basically heaters. So we'll put these servers in racks. We'll put them side by side. And in the middle, we'll create an aisle, a cold aisle. And we'll pump cold air into this area. Now, people who are a little bit more savvy about deploying their data centers will put a cap on top of this aisle so that the cold air doesn't mix with the hot air. Cold air will enter in through the servers and out after it's cooled off the components, and it'll be distributed around the data center building in the room itself. Eventually, the hot air will find its way to a device called the computer room air handler. An air handler or a crack unit may be called. This device has a filter in it, and it cleans the air. The air then passes through radiators or coils, which are devices that have cold water running through them. And the cold water then absorbs the heat from the hot air which was passed over them. The water is now hot and it gets transferred to another part of the data center, either indoors or outdoors, where we'll have chillers. Chillers are devices almost like a refrigerator which use electrical energy in order to change the temperature of the water. Water is then pumped back out to the data center floor, back to the air handlers, and the process repeats itself. Now on the bottom of the air handler you'll have a fan. The fan causes all this air movement inside of the data center, and it's basically pressurizing the floor. The floor in the data center is what we call a raised floor. It's above the concrete layer. And by pressurizing the floor, we can choose where we want to distribute cold air inside the data center. And we do that by installing tiles with perforations in them. So in this example, the perforated tile is between the racks. So how do we measure? I showed you a couple systems: power distribution, cooling systems. All of these things consume energy. How do we measure the efficiency of a data center? There's a metric called PUE, power usage effectiveness. Now, PUE is the total amount of energy going into the data center divided by the amount of energy that you're actually spending on your servers, on your IT load. PUE is really measured on the cord which goes into the server. That's more or less where the efficiency metric ends. It's really only geared to measure efficiency of data centers themselves. Okay. So how are we changing these types of model using the unique culture that we have at Facebook? One of the pillars of our culture here at Facebook is move fast and break things. Our software engineers love this. They write some code, they push it out to the site. Maybe it works. Hopefully it works most of the time. Sometimes things break. It's fun. Hardware guys, we don't get to do that. When you're playing with $1 million of hardware, I'm not going to try and break things. Another thing that we value is having a huge impact with small teams. Smaller teams allow you to communicate better. They allow you to work much more closely with your peers. You understand problems a lot better when you have a smaller team. And finally, be bold and innovate. The industry has discussed and gone over many different ways of optimizing servers and data centers to no end. But the reality is not very many companies have actually implemented these types of things. So at Facebook, we're going to be bold, and we're going to begin implementing a lot of these improvements that have been floating around the industry for a long time. We don't claim to be the original thought leader on many of these things, but we are going to be one of the few companies who actually is going to begin implementing a lot of these things which can improve the efficiency of a data center. So here's a great example of a small team. On the left, we have our data center guys. Now, that's all they do. Data center, data center, all day long. On the right, we have the server guys. Now, this isn't the entire team. This is whoever I could capture in my camera. We have a couple more people. One of the server guys isn't actually a server guy, but I needed a placeholder. And so as you can see how close we sit together and how easy it is for us to bounce ideas back and forth off one another. So the server guys have a pretty good understanding of how the data center operates and vice versa. So it allows us to be very creative. So I'll dig into some of the things that we came up with, how we're planning on tackling this problem of data center efficiency. I'll begin with power. So here's the same slide I showed you a little whiles back. It's the power distribution scheme, except now we've made a couple changes to it. The top row stays more or less the same. However, we're going to explore more efficient transformation methods. Usually by paying a little bit extra for transformers, we end up recouping that cost over the life of the transformers because we're burning up less energy inside. Now the UPS has changed completely, but what we plan on doing is rather than having a traditional UPS system with PDUs, we plan on taking voltage or power directly from the site transformers and feeding them to the servers. Straight to the server power supply, actually. And so 480 volts is the voltage that comes out of the site transformer, and that's phase to phase. If you go phase to neutral on that, you can get 277 volts. Now you might think, hey, no one really makes a power supply that operates on 277 volts. That's silly. But that's fine. In reality, most power supplies are rated up to 240 volts plus 10%, so you're already at 264 volts. To go up to 277 volts doesn't require that many modifications to the power supply. So we're working with power supply vendors in order to create a power supply that will accept 277 volts on the input. Now, the power supply does an AC to DC conversion, and if you can remember, the UPS did that as well. This has already been demonstrated, but because you have an AC to DC conversion, you don't really need to do that twice in the system. So we removed the traditional UPS, and we're going to go with a single voltage on the output of the power supply. And that would be 12 volts. Now, 12 volts is a really interesting voltage. There are many different types of battery systems which output 12 volts. And you can choose to tie a battery into the output of the power supply or interface it with the power supply itself. And by doing so, you've created a source of backup energy for the server, and you're able to eliminate the UPS completely. Not only did you eliminate the losses in the UPS, but you were also able to eliminate the cost of the UPS as well. And so that took out an easy 8 to 12% of efficiency. Because we removed the PDUs, we no longer have the transformer there. We took out 1% of efficiency, and we're also delivering power at a higher voltage throughout the data center, so you have less copper losses as a result of that. Now, the motherboard's VRMs still have the same function, but they need to be adjusted to accept 12 volts now. And that's okay, it's entirely possible. And in addition to that, we can look at the efficiency of these VRMs. 90% is good, but anything really less than 93% isn't that interesting to us. The same will hold for the power supply as well. Because we now simplified the power supply by having a single output, we're able to focus more on its efficiency. 85% really isn't that good. Anything less than 93% really isn't that interesting either. So we're shooting for something higher than that as well. Now, the VRMs will have the same functionality. They'll put out your 3.31 volts for the CPU memory, and finally the power will get to the component. So by focusing on these areas, by selecting components that are more efficient, we're able to cut out a lot of loss. If you can remember, in the previous slide, we had about 35% loss in energy. And with this type of model, we only have about 15% loss. So not only do we now burn less energy inside the data center with inefficient components, but I don't need to cool that extra heat which was generated by these components. So what does this do to your CapEx? I mentioned and I showed you how you can save money on the operating expenses by cutting down your power bill. On the CapEx side of things, you no longer need to buy a traditional UPS and PDU system. Now, we did some analysis, and a traditional system cost around $2 a watt. So if you deploy 1 watt of server, you actually had to pay for 2 watts of $2 of a UPS system in there. Now, if you go with an optimized scheme, there's a number of ways to implement this. It can cost you anywhere between 10 and 35 cents a watt. So, as on the CapEx side, it's a huge win. On a typical data center project, this can save millions of dollars that you no longer have to spend on a UPS system. So this is great. Why aren't people doing this? Why can't other companies take advantage of it? Well, I came up with this idea. It's called BYOB. And it's not about bringing your own social lubricant to a party. It's about bringing a battery to a data center. So no one really makes a data center without a UPS, and no one really makes a server that has a battery on board. It's a chicken and the egg problem. If one doesn't exist, no one's going to do that, right? Server manufacturers aren't going to build a server with a battery on board because no one really has a place to deploy that, and vice versa. But there are ways to get the industry to start thinking about this. One example could be to build a data center where you have a portion of it that has no UPS over there. Now, the data center operator can charge their customers a lower rate in order to deploy their servers in part of the facility that doesn't have a UPS. Now, the customer, if they're savvy, can go and purchase a server which has a battery on board. They'll pay a little bit more up front, but in the long run, they'll save because they're now paying less power to operate that server over a period of time. So we hope to see the industry move to a model like this. As a customer who leases space in data centers, I would welcome a change like this. So I'll go into a little bit about the cooling optimizations. I'll start off with a little bit a short primer on servers. Servers come in different sizes. They're called U's. It's a standard industry standard which defines the height of the server. 1 U is 1.75 inches. Server on the left is a 1U server, and the server on the right is a 2U server. It's twice as tall as the one on the left. So there's a couple advantages and disadvantages to each one of these models. The 1U server is very dense. So if real estate is at a premium, you really want to use a more dense server, like a 1U server. Now, what does a 1U server has? It has less space inside, so inherently you're going to use smaller heat sinks. Heat sinks are devices which remove the heat from components and create surface area so the air flowing through them takes the heat with it. Now, if you have less surface area on your heatsink, that means you need to pass more air through the system in order to cool it. In the 2U server, you can have larger heatsinks. They cost a little bit more, but they have more surface area. So you get to flow less air through the server to achieve the same amount of cooling. So this is what the fans would look like. In a 1U server, you would use a fan on the left, which is a 40-millimeter fan. In a 2U server, you would use an 80-millimeter fan like the one in the middle. And then the fan on the right is a fan that's used inside of an air handler. It's the largest fan out of all of them. Now, the physics of fans make it so that smaller fans are inherently less efficient. You have to spend more energy in a smaller fan in order to get the same amount of airflow from it. So if you had to choose, which fan would you use? I would want to use the large fan as much as possible. So really rely on your air handlers in the data center to create a pressure differential that's favorable for your servers. If you can do that, then the fans inside the servers will hardly ever have to operate. So how did we apply this at Facebook? We did an analysis. We looked at the different server heights. And we looked at 3 different things. One of them is power. And this power is how much power we're spending on airflow, on fans itself. How much does this cost? This is a total cost of ownership analysis. And we amortized this over a couple of years, over the life of the server. Then we looked at the cost of the server itself, and we also looked at the cost of the data center itself. So the 1U server on the left is an extreme case, and you'll pay the most amount over the life of the server in power to cool that particular server. On the other hand, the server is slightly cheaper because you have less sheet metal, less metal inside your heat sinks, which you're using to deploy the server. And the building is also the cheapest here. The cost of the building as represented here really represents the cost of the shell. There's a fixed cost in the building, which is all your equipment, your air handlers, your chillers, your PDUs, all of that stays the same. Now, when you go to a larger server like a 2U, you keep that equipment and you just expand the building. However, you also need to create more piping and more copper to distribute power and water throughout the building because now your servers are less dense and your building has to get bigger. So the other extreme case is a 2U server on the right. And you can see the power to cool that, or the cost of the power to cool that, is the lowest. The cost of the server is the highest. In addition to that, the cost of the building is also larger. So at Facebook, we did this analysis. We found that 1 and 2U servers are really attractive, and we actually found that there was a slight improvement on a 1.5U server versus a 2U server. So this is a concept that's also well known in the industry, free air cooling. This is a way which can let you get around using devices like chillers to cool your servers. This is the same model like I showed before. You have the 2 racks with a cold aisle in between, and if you're smart, you can contain it as well. That's nothing new. However, why waste energy on a device that's using a mechanical system to cool your water? If you build your data center in an environment which is cool for most of the year, you can just use the air from outside. So you can have a filter medium, which will clean the air going in. Use a similar fan like you would in your air handler to pressurize the floor. Flow that air through the servers, and then have another fan on the outlet which will take this now hot air and exit it outside the building. In the industry, this is commonly known as economization as well. And if you do it right, you can build this type of system where you can economize year-round and never actually have to use a chiller or spend extra energy on the mechanical work to cool your facility. We've also looked at the motherboard and the mechanics of the server itself. How did this is a typical 1U server here. How did this type of server come about? So if you think about how people started deploying servers in data centers, they took these towers, right, which was a desktop tower, something that everyone had on their desk back in the days, and they put them inside these data centers. Now, people realized that wasn't the best way to deploy things because they weren't very dense, and you could actually fit more servers in if you compacted them into something that looked like this, a one-use server. However, they kept a lot of the features that these desktop had, right? You can see it has a lot of plastic bezels on the front. It has a lot of extra mechanical, I don't want to call it garbage, but features in there which don't really provide much functionality to the overall server itself. These things create a lot of airflow restriction inside of the server, which requires you to spend more energy to move air through it. So at Facebook, we're going to look at this again, except we're going to start from the other extreme. We're going to start from the very basics, whatever is required to build out the chassis for a server. And we're going to eliminate a lot of these features. Now, a lot of these features here are here because the manufacturers need to give the customer that they're buying something that's worthwhile, right? If a customer goes and spends $5,000 on a server, they need to feel like it was worth $5,000, and it needs to look nice. But all of these features, the plastic bezels, the disk trays, all of those types of things don't really provide any functionality. And I would actually prefer to have an ugly server. To me, an ugly server is a beautiful server. It means that I paid less money for it. Now, on the motherboard itself, there are a couple other optimizations that you can do. Motherboard manufacturers in general don't know how the end user is going to be using their system. They try and make a very broad system so that it will appeal to many customers. And that's not necessarily the right way to go. Because at Facebook, we have a homogeneous fleet of servers. We know exactly how they're going to be used. We know how much expansion we need. As a result, we can remove a lot of connectors and a lot of cost from the motherboard itself. This can come in the form of removing video cards, removing extra disk connectors we don't need, removing PCIe connectors, cutting out all sorts of ICs which don't really provide us any functionality. So I talked about a little bit of how we're looking at optimizing the system, optimizing the server itself, optimizing the data center. Let's go back to this PUE metric over here. PUE, we said, measures the efficiency of the data center itself. But to us at Facebook, we're paying for the entire system. We're paying for the power going all the way from the utility to the component itself. So while PUE is interesting to us, it's not ultimately what's driving us. We're looking at the total PUE of the entire system, all the way from the utility to the component on the motherboard itself. Now, people who purchase servers don't typically have a metric like PUE. You can easily use PUE to evaluate a data center, but if I go buy a server, there's no label on the box which tell me how efficient it is. A similar analogy could be to buying a car. You look at the window sticker, it tells you what kind of gas mileage you're going to get from that car. I have no idea what kind of efficiency I'm going to get from my server unless I dig in and work with the vendor and manufacturer to really figure out what the efficiencies are in the system. But the industry in general could do everyone a service by including some sort of metric on their server so that customers can take that into account when they actually purchase a server. They don't have to guess as far as how efficient their server is going to be. So why are we here? Why do we have to have a data center and server team? If you think about companies which are going to be innovating in the data center and the server arena, you wouldn't think about Facebook, right? You would think about large server vendors, the traditional ones that you can go and buy a server from nowadays. You would think about data center operators who build these cookie cutter data centers over and over again. They should be the ones to innovate in this area. Now, what we found is that a lot of the innovation in the field is being driven by companies which do neither of those two things. They're driven by companies who have thousands of servers and who really care about efficiency of these systems. Now, these large companies are able to throw resources at the problem, right? We have capital to be able to afford engineers on hand in order to solve these problems. And that's great because now we can have more efficient systems. We can use less energy. Other large companies can do the same type of thing, but it's not really benefiting the rest of the industry. Smaller companies who might deploy less servers can't really go and purchase these efficient systems, can't go and design their own systems. So at Facebook, what we're going to try and do as we go along these developments is be more open with our architecture and be able to share more so that the rest of the industry can pick up on it. It's no longer okay just to be secretive. There's too much at stake. Smaller companies might use too much of their resources and too much of their capital on their data center infrastructure. And they should be allowed to benefit from the same type of optimizations that we're making over here at Facebook. So now I'm going to open up the questions, but before I do that, I have a couple caveats. I'm not going to answer specific questions about numbers, how much we spend on servers, how many servers we have. I'm not going to talk about the specific vendors we're working with, and I won't talk specifics about our architecture just yet. Sure. Sorry, let's get the mic to you.
The question was about flywheels and whether you are agnostic or against or for, as opposed to battery backup.
Sure. So flywheels have an inherent loss in them, and they also create somewhat of a maintenance problem. The loss is there because you need to spend energy to continually rotate the flywheel. In an optimized power distribution scheme like I showed, where you tie the battery locally to the server, you don't even really have to worry about that loss.
I'm curious if you thought about ideas of the byproduct that you have to deal with is the heat, and to recycle that in some way that it can become a profit generating.
Oh, sure. So we employ many technicians in the data center, and the idea is to take that heat and create hot tubs for them so they can soak in after work. No, but honestly, the heat that we generate is pretty low grade. It's not very hot. So to do something to pull energy out of it is a little bit more difficult. We are thinking about different ways in order to incorporate that heat into the building itself. There are occupants inside of the building. But for the most part, because of the nature of the heat, it's going to be difficult for us to do a lot of useful work with it.
Do you anticipate raising the ambient temperature in the data center?
Sorry. The question was, do I anticipate raising the ambient temperature?
80, 90, what do you
So there are ASHRAE guidelines about what you can do. Because we're taking more ownership of our server design, we can now design it in a way which allows us to raise the temperature in the data center. By raising the temperature in the data center, you can do a lot more economization, a lot more free air cooling, and improves the efficiency of the entire system greatly. No specific numbers yet, but higher than what you would traditionally find, yeah.
How are you getting support from your server vendors if you're modifying the servers that they're shipping to you, in a way where you're maybe taking off the lid and cutting stuff up? How do they react to when you're asking for support?
Sure. I think at this point, volumes are large enough that the server vendors are interested in helping us with that as opposed to opposing us with that. So we're actually being supported quite well from them.
On an operating system level, do you guys do any studies into your code itself to how does your code itself impact the PUE of your data center and the efficiencies of the components themselves?
So you're asking a hardware guy software questions, but I'll take a stab at that. We definitely look at the energy consumption of the servers, and we look at that in real time. So we run when evaluating what type of hardware we're going to purchase, we actually look at the power consumption over a period of time in which we ran actual code on there, and we can make optimizations to the code to try and cut down that power a bit. Yeah, did you have a...
Specifically, are you taking advantage of any like offload ASICs, or do you look at, I can do this code in software and whether it's X amount of CPU cycles versus the cost of investing in an ASIC?
Right. So the question was, are we looking at ASICs to offload some of the software work to do things in hardware itself? Answer to that, I'm going to have to be a little general, but we're looking at all different sorts of architectures. We're not limiting ourselves to traditional server architecture at this point.
So I'm curious about the safety aspect. 480 volts will kill someone.
So that's a bit of a challenge, right? When you distribute 277 volts, most equipment out there is really only rated up to 240 volts, and that could potentially be a showstopper. However, we were able to find a lot of different components that are rated beyond that to 300 volts. And as long as I don't want to risk the safety of anyone in or around the data center, and so we're sticking with UL certifications on anything that has high voltage there. So I think their answer is we feel comfortable that we can find equipment which can handle that safely.
So just along the same lines, what kind of battery chemistries are you looking at? Because having lithium-ion batteries, pushing that kind of power into them could be really dangerous. So
sure, looking at different type of battery chemistries. And what's driving that, I won't give you specifics as to which one we're leaning towards, but it's just pure cost at this point. Some technologies are more developed than others. Some technologies are easier to handle, to maintain, and to monitor. And we tend to lean towards those.
Have you had any experience or getting your data center vendors to give you like real metered pricing rather than flat rate pricing, so that you can shut servers down or put them into lower power modes during idle times and then bring them back up to full power later?
Sure. So we're at the scale where we no longer lease cages in data centers or rooms. We lease the entire building at this point. And when you get to, and data center operators typically do a pass-through on the bill, so we pay for every watt that goes into the building. So anything we can do to optimize on the data center front actually is savings in our own pocket, not in the data center operators.
What do you find the immediate environmental impact to be on a closed air system versus open air system?
So environmental impact of emitting the heat directly into the environment outside. So in the end of the day, the heat ends up outside the building somehow. If you're going to evaporate water, if you're going to run a chiller, you generate heat and that gets emitted into the environment around the building. On an open air system, you're inherently using less energy and thereby emitting less heat into the environment. How that impacts the environment, I'm not quite sure yet, but I know it'll be less because we're emitting less heat.
How do you think multi-core and OpenCL is going to change your environment?
So multi-core is something that we're already, obviously a lot of the large chip manufacturers have implemented multi-core. It allows us to run more optimized code. Going to more details than that, I guess in general I would say we find our software to be more efficient when we have more cores.
Any guess on what fraction of power goes to compute versus interconnect, network versus disk storage?
Disk storage, interconnect is relatively small compared to the compute power itself. If you look at a motherboard, the energy hogs are the memory and the CPU. Interface card might only take a number of watts. We do have a couple larger routers in the system, but they're serving hundreds and hundreds of servers. And so for the most part, we find that power going to network is negligible compared to the actual server workload. And so our optimizations are really going for the low-hanging fruit, for the servers first.
So you mentioned moving your data centers to maybe colder areas. So are you looking at any sort of specific area, in the northern hemisphere? And then if you are deciding to do that, maybe it's in Canada. I mean, usually there isn't very good network connectivity into the internet in some of those areas. So how do you deal with that?
Yeah, so I can't help you hedge on real estate markets here. But the general idea behind a data center site selection is you need power, you need fiber network connectivity, and you need a favorable climate. I'm not going to go into specifics about where we found those things, but we have found areas that have all of those things. Yeah.
We'll do one more question after this one.
With the server optimization that you were discussing and removing connectors and everything else, how likely is the serial console connection going to stay on the servers for remote management, et cetera?
Serial console is actually something very interesting. It allows you to take out a video connection, which helps in the overall cost of the BOM and software licensing fees for whatever's driving that. The technology's been around for a while, and it's proven to work well, and people tend to stick with it, and it's something that we stick with in the meantime.